Welcome to today's lesson, which is called linear programming. Linear programming is a process used to optimize applications in business and economics. If a linear programming problem has a solution, it must occur at a vertex of the set of feasible solutions. When we're solving a linear programming problem, first we sketch the region based on the system of constraints. Second, we find the vertices of the region. And third, we test the objective function at each of the vertices and select values that optimize the objective function. For a bounded region, both a maximum and minimum will exist. For an unbounded region, if an optimal solution exists, it will occur at a vertex. Example 1. Find the maximum value of z equals 3x plus 2y. This is our objective function, subject to the following constraints. X is greater than or equal to 0, y is greater than or equal to 0, x plus 2y is less than or equal to 4, and x minus 1 is less than or equal to 1. Now remember, we have to start by first sketching the feasible region. So we want to rewrite these inequalities so that they're solved for y. So x plus 2y is less than or equal to 4 becomes y is less than or equal to negative 1/2 x plus 2. And x minus y is less than or equal to 1 becomes y has to be greater than or equal to x minus 1. So now we'll graph these inequalities. Now we'll list the vertices. We have one at 0, 0, one at 1, 0, one at 2, 1, and the last at 0, 2. And then we'll test the objective function. Now the best way to do this is to set up a table where one column are the vertices, then we have the objective function 3x plus 2y, and then we have the value of the objective function. I went ahead and filled out the table for you. When we look at the numbers here, we're trying to find the maximum value. Well, you can see right here that the maximum value we get is 8. So we can say that we have a max of 8 when x equals 2 and y equals 1. Example 2. Find the maximum value of z equals 4x plus 2y subject to the following constraints. Again, we'll start by sketching the feasible region. Before we can do that, we want to solve all these inequalities for y. So this becomes y has to be greater than or equal to negative 1/2 x plus 2. This becomes y is greater than or equal to negative 3x plus 7. And this is y is less than or equal to 1/2 x plus 3.5. So I'll go ahead and graph those for you. So now that we've drawn the constraints and sketched the feasible region, you can see that we don't have a bounded region. When this happens, it means that we are not guaranteed to have a maximum or a minimum. But if we do, the max or min will happen at a vertex. So let's go ahead and list our vertices. We have one at 2, 1, one at 4, 0, and one at 1, 4. So we'll go ahead and we'll make our table where we put in our vertices, our objective function, and the solution to our objective function. I'll go ahead and fill in the table for you. So when we look at the table, our least value is 10 and our greatest value is 16. But because the region is unbounded, we are not sure if 10 is our minimum or if 16 is our maximum. So what we need to do is we need to pick a point somewhere up here in the feasible region and see what happens when we plug it in. So I'm going to choose the point 5, 4. I know it's not a vertex, but I'm just going to put it in our work. And when I plug in 5, 4, I get 20 plus 8, which is equal to 28. Now 28 is bigger than 16, which means 16 cannot be a maximum. So there actually is no maximum. But we have a minimum of 10 when x equals to and y equals 1. So our first two examples were just kind of trying to show us the mechanics of the process, but really these kinds of problems are only beneficial in the context of a word problem. So example 3 says a candy manufacturer wants to maximize the profit for two types of boxed chocolate. A box of creams yields a profit of $1.50 per box, and a box of nuts yields a profit of $2 per box. Market tests have indicated the following constraints. 1. The combined production level should not exceed 1,200 boxes per month. 2. The demand for a box of nuts is no more than half the demand for a box of creams. And 3. The production level for creams should be less than or equal to 600 boxes plus 3 times the production for nuts. So the first thing we need to do is define our variables. So I'm going to let x equal number of boxes of creams and y equal the number of boxes nuts. Now we want to write our objective equation that allows us to calculate profit so that we can maximize profit. So our profit is going to be equal to $1.50 per box of creams, or 1.50 times x, plus $2 per box of nuts, or 2.00 times y. So basically we can say P is equal to 1.5x plus 2y. Now we need to look at our constraints and write equations for our constraints. Well, our first constraint, the combined production level should not exceed 1,200 boxes per month. So that means that if x is all the boxes of creams and y is all the boxes for nuts, x plus y has to be less than or equal to 1,200. Our second constraint says the demand for a box of nuts is, a box of nuts is y, is no more than half. That means it has to be less than or equal to 1/2 box of creams, which is x. And then finally, our third constraint says the production level for creams, x, should be less than or equal to 600 boxes plus 3 times the production for nuts, which is y. Let's go ahead and solve all these equations for y. Now that they're both solved for y, we also have to consider the fact that we can't make negative boxes, so x and y have to both be greater than or equal to 0. Now we need to graph these equations. To save time, I went ahead and I graphed these on a graphing calculator. So here's the graph, and you can see that we have 4 vertices. So I'm going to list them. 0, 0, 600, 0, 1050, 150, and 800, 100. So since this is a bounded region, we should be able to find our maximum profit at one of these vertices. So we'll set up our table. So we can see that we have a maximum profit of $2,000. This means that our max profit of $2,000 occurs when production of creams is 800 boxes and 400 boxes of nuts. That's all for now. Thanks for watching.